but we should probably leave a few minutes for you to ask questions of Chip and myself. So please go ahead and do so.
There was one. Oh, go ahead.
The efficiency curves, was that electrical input power to hydraulic power?
Power measurements were made with torque sensors, torque times RPM in the output shaft. And the affinity curves were calculations based on the relationships of power and cubic relationship of power. One other thing, linear actuator. This is one size, which is a little bit larger than we actually need for that size. This will allow you electrically to vary the position of the control arm and totally automate and close the control loop, as we would say, based on either pressure, flow, or even maintain a constant speed if you needed to do that.
What about the heat generated from the induced currents? Saw those heat.
Really, yeah. The fins, design of the fins is such that, well, let's just start with full torque and speed. With slip design is about 1.5% of slip, so that's about 20 RPM. And if you took a feel last night of the exhaust air coming off of the fans, you didn't feel any heat whatsoever on that. Those fins are designed for the maximum heat generated would be at about 33% slip based on slip heat equations. They're, again, a theoretical calculation. And we oversized the fins for that condition as well as a lockup condition to try to keep the rotors so we would never reach any point of where aluminum becomes molten, which is well up over 1,000 degrees. Now, we've tested this, was it Rich, almost 500 degrees just to make sure all of our slide mechanism, nothing bound up, and everything's been fine. And our operating point for, let's just say, exhaust air coming off of that, we've never really achieved more than 120 degrees at the maximum slip condition. So.
Is that material brass?
No, it's aluminum. The fins themselves, you mean?
The one that looks like brass.
Oh, the can's actually steel, and that has to deal with completing the magnetic circuit.
Absolutely, because the magnets need a return path, and steel provides that. Therefore, there is no leakage of flux outside the device, no danger of it contaminating your environment in any way.
Yes?
Talk about manually setting that was the left. Is there any tendency for that setting to migrate either engage more within the cylinder or outside the cylinder? Or once you set it, is it going to stay there?
Well, if it's a manual setting, we'll have an actual jack screw or setup that'll hold it right where you want it. As you saw last night, with the torque on the torque rods that are internal to that the rotor's sliding on, it does seem to stay fairly close. There is a natural tendency for it to want to go to the full in position. Sort of like any magnetic field wants to center itself, but the torque is also involved, so it does stay pretty constant to where you set it, but it will be fixed manually, rigid.
Would you say alignment is probably less important with your device?
Yeah, we just made, well, that unit installed at the aquarium has a flex plate design on the motor side, and internal to the can is an angular adjustable needle bearing. So we can actually call that shaft what they call a floating shaft or spacer shaft. Spacer shaft alignment, you're allowed about 1,000th and a half per inch of shaft. So let's say the shaft's 10 inches, so that'd be 15 thousandths of offset allowed. So the alignment standards are probably in the order of 4 to 5 times more alignment than would normally be allowed on a flexible coupling. And what our goal is to have an alignment adapter or pin that you can check the alignment that your air gap spacer or air gap would be maintained. We've designed around about a 70 thousandths air gap. So if we're off 15 thousandths in the air gap, we do not generate any excess vibration. And what did you say, Rich? That was off last night, running at about 5 or 6 thousandths of offset alignment. And we've done checks on more angularity, and the flex plates that are in there, similar to our Thomas coupling, if you're familiar with that type of Rexnor Thomas. maintains your radial position of the rotor without any run out, and is very stable. It's a positive coupling, it really can't fail. And if you ever do really seriously misalign it, you'll actually see the plates bend. And I've seen the plates bend a lot, and if people have seriously misaligned that type of coupling and still run with time. So we would hope that people could be a little closer than that.
That would be the key if it's to self-destruct without alignment a little bit.
Yeah, the Thomases are very, very good, that type of design. It's going to be our own design coupling. It'll be part of the unit. Yeah, go ahead.
Once you set the device into specific speed and load, how would the increase in load affect the slip of the device?
Well, if you look at the torque curves, let me see if I can get them back. On this one here, as load changes, let's say you set the engagement to 50%, whatever. So you're naturally traveling on one of those curves. Let's say it's the green curve here. So that is in fact the characteristic of that particular device at that setting. Now, assuming you change the load, or the load changed by itself, what will happen is it requires more torque or less torque. So the amount of torque will be one of these values here. And it could be any value depending upon the torque, the load requirement. And it will automatically settle to the speed that is one of the points on that curve and continue to run at that new speed. You don't have to do any adjustment. Now, if you come along and say, I don't like that engagement, and change it to a different engagement, 100%, 80%, it will seek another point because you made it move to another curve. So you can leave it alone, it will look after itself, but you can also interfere with it and make it better.
And I think a lot of people will close the loop on the control and go for a pressure or a particular flow rate on that. One thing that's worth noting just before we finish, people look at a frequency or electronic drive driving a motor and conclude that the device is saving energy because the motor shaft is slowing down. And that's not what's happening. The power to the motor is being changed and manipulated by the electronics, which is fine. In our case, our shaft is running at constant speed, the motor's running at its best efficiency point, but the current is being decreased, therefore the current times the voltage is the actual power being consumed. It's a different way of doing it. I would say the big advantage is that you're not slowing the motor and reducing the cooling effect on that motor for those slower speeds the way that an electronic drive would. We keep the motor running at its best efficiency and temperature during that whole change in power.
Any other questions? Well, thank you very much, ladies and gentlemen.